So we have Fourier series in discrete form can be written as ik omega naught Tn. Well, this is bad n. Tn is just the points here, point at which we measure the value of the actual function. So when you look at this is really long. So since we're using n is a total number of samples we've taken. So if we go from 0 to n minus 1, we have n in total. So to simplify this equation, we can write it in, just use the small n just to be to go with capitalized N. N is just the number of samples we take. And the reason why we can do that, we can just see from this graph, if we have changed the x-axis to capitalized N, total number of samples we take, then the stuff here becomes, was T1, now it's just 1, now it's just 2, 3, 4, and 5. We take, and that makes it easier because it's just a changed time into just the index 1, 2, 3, and 4, 5. It means the same thing because now we have at this point f of 1, at this point f of 2, this point f of 3, etc. We have the same function just with the index n. So now we have this. What else is different from in discrete time than continuous? Recall in continuous function, omega naught is equal to 2 pi over the period t. So in here we don't have a period. All we have is n, the total number of samples we take. So when you look at this, it's not very periodic in this sense, but if we can just look at it as the whole from 1 to 5, we can just look at it as a period. And we can imagine this graph, this part of the discrete graph, repeat itself from negative infinity to infinity. Other than this interval, we can just say n is the period of this discrete function. So if we do this, it seems reasonable that we can do omega naught is equal to 2 pi over n for our discrete time. So with that, we can substitute into the series. Omega becomes 2 pi over n times small n. So now here we have this. All the variables are in terms of discrete. So this is the sample number, and this is the total number of sample, this is sample number, and but we have k. The summation is of k. K is the constant that makes the base frequency, which is omega. This whole part makes the harmonics of the sine and cosine, which is in E, and K also assign a coefficient for each of the harmonic of this frequency. So this is summation of k, but now we have two n here. Small n and big N, they are obviously related. So what if we want to find out the relationship between n and n? Then we need a summation of n. We need something like this. Summation of n from 0 to n minus 1. If we're looking for that, what's in the summation then? So to make it simple, we can just have the negative exponent to the e. So we know that's gonna, when we multiply them together, they're gonna cancel out. So if we have e to the negative I k 2 pi over n. When we multiply this thing on this side and on this side, we're gonna have something like summation of e to the negative I k 2 pi over n times the function f of n, just put it in the parentheses so you know, and times the summation of that. Negative I k 2 pi over n. We can simplify this into summation k 0 and minus 1 summation n 0. Notice that we now have two different summations, so we take account of n as well as k. Ck e to the ik 2 pi n times e to the ik negative n. Notice these two parts, when we multiply this together, we get 1 because exponent goes to 0. So the summation now becomes k equal to 0, n minus 1. Since this is in terms of k, so we're just gonna put the ck in here. Now the summation of n is equal to 0, n minus 1 of 1. Then we have the summation of k equal to 0, n minus 1, ck. This summation is equal to n, so the whole thing is just n, the total number of samples we take. Can pause here.